speak about local to global principles in integral circles patterns.
Okay, thank you so much for the introduction, and thank you for the organizers for organizing this great workshop. It's a pleasure to be here. So before I forget, all that I'm talking about today is joint with Kate Stang and Shen Zhang. So the problem that I want to talk about is motivated by a problem in Apollonian circle packings. Just historically, that's how it happened. And I know Alex already talked some about these, but just to remind you, the construction is you start with 4 pairwise tangent circles like this, one on the outside, and then into each one of these little regions here, there's a unique way you can inscribe another circle. That's the theorem of Apollonius, hence the name Apollonian. So you do that, and then you can iterate this process. So into every one of these little areas, you inscribe yet another circle. And if you can continue that indefinitely, you get a packing of infinitely many circles, which is called an Apollonian circle packing. So the number theoretic interest in these comes from the fact that if you have that any 4 circles that are pairwise tangent to each other in the packing have integer curvature, or 1 over the radius, then actually all of the circles in the packing will have integer curvature. So here there are 2 examples of such integer packings. You can sort of not worry about this little minus sign on the outside here for now. And there's infinitely many such integral Apollonian circle packings, and in fact, infinitely many primitive integral Apollonian circle packings, by which I just mean the GCD of all the curvatures of the circles is 1. And from now on, I'm assuming all packings I'm talking about are primitive in this sense. Okay, so you can ask lots of questions about number theoretic questions about these. And so one observation is in these packings, if you look at the set of curvatures reduced modulo 24, then the set of residues you get for the first packing is right here, 2, 3, 6, 11, and so on. And for the second one, you get 0, 4, 12, 13, 16, and 21. So you won't get all the residues, some subset. So I'll tell you why on earth we should consider this mod 24 in a moment. But a natural question is, do these obstructions mod 24, given that 24 is somehow a significant number for these things, completely describe the curvatures that come up in the packings? So is it true, for example, that, say in this packing, whenever I have an integer that's 2 mod 24, perhaps if it's large enough, is it true that that integer is necessarily going to be a curvature in that packing, just because it's 2 mod 24? Okay, so how do we attack this question? Well, it goes back to a theorem of Descartes, which says that if you have A, B, C, D are curvatures of 4 pairwise tangent circles, and they satisfy this quadratic equation, 2 times the sum of the squares minus the square of the sum is 0. And in order for this to be true, if one of the circles is internally tangent to the other 3, then you take it to have negative curvature. Okay, so from this theorem, and I think Alex actually described how, you can derive the following fact. That one way you can describe the curvatures in the packing is, so you take a vector of any 4 curvatures of 4 pairwise tangent circles in the packing, and then the set of all quadruples of pairwise tangent circles in the packing is going to just simply be precisely the orbit of a group A acting on V. So A is going to be a subgroup of the orthogonal group fixing this Descartes quadratic form here. And so it's sitting inside GL4Z. So just matrix multiplication. You get all of the quadruples of curvatures of pairwise tangent circles. Now I'd like to tell you a few things about this group A that will be sort of significant going forward. So we call it the Apollonian group, and it has the following properties. So first of all, it's of infinite index in the whole group OQZ. So it's small in that sense. But it's large in the sense that it's Zariski dense in OQC. Okay, so Zariski closure in GLNC, GL4C is OQC. These 2 things put together signify that A is what we call a thin group. By thin, I just mean, so let's say if I give you a subgroup of gamma of GLNZ, what I mean for it to be thin is that if I take its Zariski closure in GLNC, G, then gamma will be infinite index in the intersection of G and GLNZ. So in this case, G is this OQC and gamma is A. And the intersection of G and Z is OQZ. Okay, so the other thing I'd like to tell you is the preimage of A under the spin homomorphism. So if you don't know what this is, then it's not too important right now, but if you do, that's great. From SL2C to SOR31, so the quadratic form Q is of signature 3,1, is a subgroup of SL2Z adjoin I, and it contains the principal 2 congruent subgroup of SL2Z. Okay, so that's another important little thing to know. Also, if you consider this image sitting in SL2Z adjoin I, this preimage, and you reduce it modulo primes p, just prime integer primes p, you're going to always reduce either into this group or into this group, and it's actually going to, the image is going to be onto for all primes except for 2 and 3. So this is where the 24 is coming from. So 24 is 2 cubed times 3. So it turns out that this group basically only has this kind of obstruction modulo 2 and 3. And if you want to know how high up this obstruction goes in the powers of 2 and 3, it turns out that for 2, once you know the image of the group mod 2 cubed, you can just lift naturally to the image mod 2 to the 4th and 2 to the 5th and so on. And for 3, this happens at the first power. So that's where the 24 comes from. Okay, and the last thing I'll mention is just the generators of the group. So this group A is generated by these 4 matrices, which are inversions. The only thing really I want to note about these for the purpose of this talk is just that, so if you look at any one of these generators, what they do is when you multiply it by the vector A, B, C, D, you're fixing 3 of the coordinates and changing the other one. So S1 fixes the last 3 and changes the first one. S2 fixes changes the second one, and so on. Okay, so coming back to my question about this sort of local to global type principle. So there's a conjecture which goes back to, not quite in this form, but originally was stated in some form by Graham, Ligarius, Mallows, Wilkes, and Yan in 2005, which was really the first paper on number theory of Apollonian circle packings. And then in this form it's stated in a paper of mine with Sandin, in which we sort of try to show heuristically why it seems to be believable. Okay, so take O to be an orbit of A corresponding to a primitive integer Apollonian circle packing, and then take O24 to be the set of residues mod 24 that you get when you reduce all the curvatures mod 24. So we saw 2 such sets for those 2 packings I showed you in the beginning. So the conjecture says that there's some big number, x sub O, such that if you take anything bigger, whose residue mod 24 lies in the allowable set mod 24, then it must be a coordinate of some point in O. So it's exactly the sort of thing that I implied we would hope to be true. For example, in that first packing, any big number that's 2 mod 24 should be a curvature. Okay, so this conjecture, as stated, is still open. So first step towards this is a very much weaker statement. So notice that in particular what this conjecture would imply is, so for example, if you know that every number bigger than 1 million or something that's 2 mod 24 appears as a curvature in that first packing I showed you, that means that at least 1/24 of all integers appear in the packing. And clearly, if you have this conjecture, then you get that a positive fraction of all integers should appear as curvatures in any packing. So this is what we proved together with Bergan quite a few years ago. So we call this number kappa. This is the number of distinct integers less than x, which appear as curvatures in the packing that corresponds to this orbit. So we show that there's some positive constant such that kappa is greater than x times that constant. Okay, and then the closest we've come to proving this conjecture is this theorem of Bergan and Kantorovich, which says that, well, so they call a positive integer admissible in an Apollonian orbit O if it is in O24, mod 24. And they denote by E sub n the set of admissible integers less than n that are not coordinates of some point in O. So you expect them to be coordinates of some point in O, but they're not. So what the local global conjecture on the last slide would imply is that there's some bound independent of n on E of n for all n. There's finally many such numbers that are sort of admissible, but they don't appear. But they show that E of n in size is at most n to the 1 minus epsilon for some positive epsilon. So that's basically saying that those integers that violate this local to global principle make up a zero density subset of the integers, not necessarily finite though. Okay, so I'd like to kind of say what the main strategy behind both this theorem, or the proof of this theorem, and the one with Bergan and myself is, just because that's the strategy that we'll be moving forward with to prove something more general. Okay, so there was an observation of Peter Sarnax back in 2007, which he wrote up in a letter to Ligarius about the Apollonian group, which is that you can so consider the following subgroup of A. So I'm just looking at all the generators except for the first one and seeing what I get. And the thing is that, remember, what the first generator does is it changes the first coordinate somehow and it fixes the other three. But these last three generators, they all of them fix the first coordinate. So really what this is doing, if you look at the orbit of A1 times V, you're just doing something to those last three coordinates. Okay, so I have this little picture that's trying to summarize what's going on here. So A is a thin subgroup of OR31. And then you take this A1, which is a subgroup of A, and these are both sitting inside of OQZ, where Q is a Descartes form. Now, because A1, so somehow morally, it's like a subgroup of GL3Z, because it's really only working with those last three coordinates when you act on V. You can change variables in an appropriate way, so just conjugate A1 to get a group, A1 prime, which is isomorphic to a subgroup of OR21, so sitting inside GL3Z, fixing this quadratic form here, so B squared minus AC. And then there's a spin homomorphism from SL2R into OR21. And you can consider the preimage of this group under the spin homomorphism, and you just simply get the principal 2 congruent subgroup of SL2Z. Okay, so you have this started with this thin group A, and then you took this smaller group A1, which turns out to be actually this nice congruent subgroup, really, but inside of a smaller group than what you started with. And so what that enables you to do is, well, in particular, so we know if we have a kind of formula for rho, and we know exactly what the matrices in gamma of 2 look like, and that will tell us exactly what the matrices in here look like. So what I'm saying is, if I have this kind of element in gamma of 2, then the formula for rho, or G, of this form in gamma of 2, then the rho of G looks like this. And now if you just think about, of course, this is in this group A1 prime, which is not A1, so I'm really interested in the orbit of A1 acting on V. But if you just think about what happens if you take this and multiply it by a vector x, y, z, say in the first coordinate you'll have x alpha squared plus 2y alpha gamma plus z gamma squared. So as alpha and gamma vary, this is going to be give you values of this binary quadratic form in alpha and gamma with coefficients x, 2y, and z. And somehow we know pretty well what kind of integers are represented by binary quadratic forms. So it's nice that we've reduced this to this binary quadratic form situation. And if you look at all of the coordinates of the orbit that you get here, you'll actually just simply get, I mean, here alpha and gamma, they're coming from this group, so it's not just any alpha and gamma, they're relatively prime to each other. But if you look at all the coordinates that you get here, you'll actually get simply all the values of some binary quadratic form. And okay, if you change the variables back into this A1 situation, what you're going to get is that the set of integers appearing in this orbit are all of this form. So it's some binary quadratic form, f sub a naught. This big A naught, B naught, and C naught depend just on these integers here, minus A naught. So there's a shift of A naught. And the idea then, both really in my paper with Bergan and Bergan-Kantorovich, is that, well, so here you're just looking at this orbit of this very small subgroup of A. Why not, instead of taking E1, take what we might call A2, so all but the second generator, generated by all but the second generator, in which case you'd be fixing the second coordinate, and sort of mix those two together over and over again, and what you'll end up with is actually an infinite family of such binary quadratic forms, shifted by some shift, representing some integers. And you can hope that once you take the collection of all these integers, you will collect a positive fraction of all the integers or something like this. And notice that the shift here is very important, because if I didn't have this shift, then taking a bunch of binary quadratic forms and seeing what I get wouldn't really get me anywhere. It would just kind of get me something like sum of two squares or something like that. But together with the shift, it makes the sets these guys represent quite different from one another. So that's important. And so again, this strategy is behind the proofs of both of those theorems. So a possible natural question is, to what other thin subgroups of OR31 do these arguments kind of apply? And that's the question we started with. And then we realized maybe it's not the most natural way to ask this question. And let me try to, in one slide, just explain why it's not the most natural way to ask it. And the idea basically is just that there's this sort of arbitrary kind of change of variables that you do from your subgroup of OR31 to get into this nice OR21, and it's just not very natural. But here's maybe an explanation. So Shen Zhang proved a local to global theorem in his thesis for these kind of packings. So this is called the Apollonian 3 packing. And what you do here, so you start with 3 tangent circles like this. And then into every little interstice here, instead of inscribing one circle like in the Apollonian packing case, you inscribe a cluster of 3 that are tangent to each other. And again, there's a unique way of doing this. And you keep doing this, and you get this different kind of packing. And there's a lot of analogies between these kind of packings and the classical Apollonian circle packings. So the relevant group, kind of like the Apollonian group, sits inside of an orthogonal group fixing a 3-1 form, which looks like this. Okay? And what is the analog of the Descartes theorem here? Well, so this time, instead of taking quadruples of circles, the natural thing to consider, or a natural thing to consider, is sextuplets of circles. So here's 1, 1, 2, 3, the 3 that you started, and these 3 that you inscribe here. Now, they're not all pairwise tangent to each other, but any one of those 6 is tangent to 4 others, and not tangent to another. Okay. So if you take such 6 circles, then you get, first of all, that A plus D is equal to B plus E is equal to C plus F. So here I'm pairing up the circles that are not tangent to each other, is what I'm doing. And that's all the same number. It's even, 2 times G. And you get that this Q tilde of A, B, C, G is 0. So actually, if you're looking at the orbit of this subgroup of OQZ acting on this kind of vector, that last coordinate isn't even representing a curvature anymore. It's representing like a linear combination of the curvatures. And as you look at other packings, for example, Kate Stang has quite a few examples of other kinds of packings. It turns out that, first of all, there's various choices of Descartes form you can choose, or analog of Descartes form. And second of all, if you look at what you're getting in the orbit, it's really no longer curvatures at all, but again, some kind of linear combination of them. And it's quite conceivable that if you work with some choice of Descartes form, this method of proof about local to global principle won't apply, but some other choice for Q you will be able to work with. So it's sort of not a very natural way to go. So what is a more natural way to go? And sort of in the spirit of Alex's talk, sort of finding kind of how geometry gives rise to arithmetic. So we'll start with an imaginary quadratic field, Q adjoin root minus D. OK will be its ring of integers. And here's the kind of Apollonian group. I'm going to refer to it as the Apollonian group. We're going to consider, so A is going to be a subgroup of SL2 OK, which is thin. It doesn't have to be thin, but somehow this is more interesting for thin groups. So we're going to assume that following things. A is not contained in SL2R. Okay, so it has complex entries. A is Zariski dense in SL2C. Then we will also assume that A is geometrically finite. So if you look at the fundamental domain you get, if you look at its action on H3, on the hyperbolic 3 space, you should have finitely many sides. And then SL2Z intersected with A contains a principal congruent subgroup of SL2Z of level L. So in the natural Apollonian case, this OK is Z adjoint I. We know it's Zariski dense. It is also geometrically finite. And this level L in the Apollonian case is just level 2. OK, so how do you get integers and circles out of this? Well, SL2OK acts on C via Mobius transformations. Let's see. So what we'll do is, so gamma in this SL2OK, any such gamma sends this sort of shift of the line of the real line to a circle or a line in the complex plane. The delta here is a discriminant of the field K. And the reason we do this is just so that we get this nice binary stratiform setup that we're looking for. OK. And by circle packing associated to A, what for now we'll mean is circles that are images of, so you can consider this just the Apollonian group A acting on this real line and see what circles you get. We will also allow to act on those circles by some Mobius transformation in SL2OK. OK, so just as a picture, so here is what's happening in the Apollonian circle packing case. This shifted real line, if this is the real line, is this one right here. What you see here is just, without what's inside the circle, is just a strip packing. So starting with 2 parallel lines, tangent infinity, and 2 circles of curvature 1 in there. And so what happens is that if you take the usual Apollonian group and you act on this line, well, you won't quite get all this strip packing, but you'll get some subpacking of it. And then, in order to get to these other packings, so it turns out one thing that Kate Stang discovered is that I don't think she was the first one to discover it, but she has written about this concept at length. But the fact that, in fact, if you consider the image of the real line under the full SL2 Z adjoint I in this case, what you'll get is you'll actually find all integral Apollonian circle packings in the following sense. So for example, in here, you're going to get this packing minus 1, 2, 2, 3. Then in this circle, there will be some other packing. And then in each little circle, there will be some other Apollonian circle packing. So that's what happens if you take this real line and you just look at the image under all of SL2 Z adjoint I in this case. And what we can do is to get from the strip packing to one of these other packing, we just transform by some Mobius transformation. OK, so that's this kind of more geometric setup of this kind of group action. And so what we're trying to study is the curvatures of the circles that come up in this packing. Well, it turns out that if you look at the curvature, it's quite simple to write down the formula of a circle that you get, of the circle you get after acting by m gamma on this shifted real line. You'll get a multiple of square root of minus discriminant, so you can just scale by that. So you just get integers. K will be an integer in this case. So this is the set we're interested in. That's the set we want to prove this local to global principle about. OK, and m here is fixed throughout. OK, and here's sort of a funny way to write this. But so we know that A contains this congruent subgroup of level L sitting inside of SL2Z. So naturally, A is just equal to A gamma of L. And the reason I've written it this way is that then, so I'm going to write every element of A as some element of A gamma times gamma prime. So I'm actually going to allow myself to run through all the elements of gamma of L, and then all the elements of A, and in the end, I'll certainly cover all the elements of A in this way. And if you look at the curvature of this circle, it looks like this. So you have the square root of minus discriminant, and then you have absolute value CA plus DC, plus the 2 times the imaginary part of conjugate C times D. A, B, C, and D, these capital guys, are just what M gamma is. So these are going to be some sort of complex numbers. And gamma prime is this A, B, C, D in gamma of L. So little a, b, c, and d are integers. So whenever you fix this M gamma and just let these guys vary, what you're getting here actually is a binary quadratic form with this shift here. So if these guys are fixed, you're getting a binary quadratic form in A and little a and c, shifted by this 2 times imaginary part thing. And those are precisely the binary quadratic forms that we saw coming up in this slightly different way before. Okay, and so if we just study the integers represented by all these shifted binary quadratic forms, looking at all these different M gammas, that is going to be exactly the set of curvatures that we want to study. Okay, so what is our theorem then? So if you have an Apollonian group A as described above, and P is, let's say P is a circle packing associated to this group in the sense I just described, and S is a set of integers appearing as curvatures in P, I'm going to call the set of admissible integers and all those integers less than big N, which are in S mod M for any M. So I'm sort of avoiding stating exactly what the congruence obstruction is here. There is going to be some number like 24 associated to any such packing, but I'm not specifying obviously what it is here. So again, En will be the subset of An, which is not an S. So you expect it to be a curvature just based on local conditions, but it's not there. So we prove that there exists an epsilon greater than 0 such that this exceptional set is of size at most n to the 1 minus epsilon. And just so you know, the size of the admissible set is some constant times n, some positive constant times n. Okay, so this is basically a generalization of this theorem of Bragin-Kontorovich's. And we think really for now, with the methods that were used there, this is sort of the most general that you can do in some sense. So those conditions on A really are pretty necessary. Okay, so here's an example of another packing, which I think maybe possibly Alex may have shown this packing. It's the cube octahedral packing in his language of a packing to which this implies. So here you have much bigger clusters of touching circles than either the Apollonian packing or the Apollonian 3 packing. So the corresponding Apollonian group is the intersection of SL2 Q square root minus 6 generated with the group generated by these guys. Now you notice there's some denominators here, which I didn't mention before, but actually you can allow your group A to have terms with denominators as long as the denominators are bounded above. So, but I didn't want to deal with the technicality of how you deal with that, but you are allowed to have sort of denominators that are bounded by something throughout the group. And in this case, this group A contains the principal congruent subgroup of level 6. So for this particular packing, we were able to prove such a local to global principle. And I think actually for all the packings that Alex and Alex Kontorovich and Kei Nakamura have, this theorem would also give a local to global principle. Okay, so how does one go about proving this? Well, I'd like to give you kind of a sketch of that. So you have this, these binary quadratic forms. So I've divided out by the square root of minus discriminant because that's what we do in that set of curvatures. So you have this binary quadratic form. And what you're interested in is we're looking at this representation number of little n. So what is this? Okay, so I have sum over all gamma in f sub t. So I'm not going to define what f sub t is for you, but basically just think of it as a region inside the Apollonian group, some growing region. So t is some growing parameter. Then I'm summing over all x, y, and z such that Lx plus 1, Ly are relatively prime. So the big L, remember, is the level of this congruence group that's contained in there. And basically what this is saying, so I'm going to plug in this Lx plus 1 and Ly into this binary quadratic form here corresponding to m gamma. This is just simply here to tell you that this Lx plus 1 Ly are supposed to be coming from this congruence from basically the A and the C entry in this congruence subgroup. Okay, so this is looking whether or not n is represented by this binary quadratic form. This is not something really to worry about. It's some smoothing function. And so what I'd like to show basically is that for almost all n, this representation number is positive. Okay, and here, if you're interested, t is a very small power of n, like 1 over 200 or something is fine, and x is square root of n over t. Okay, so, right, so I already said this. We want to show that Rn of n is positive for almost all n. Okay, so how do we do this? Well, we look at the Fourier transform of Rn, so we get this expression here. I've now sort of taken away these smoothing functions just to look nicer. They are still there. But the idea is that this is somehow easier to work with, and then you can use a Fourier inversion formula to get back to your actual Rn of n, which is just going to be this integral from 0 to 1 here. Okay, and so how do we evaluate this integral? We use the circle method. Okay, so the philosophy here is that most of the contribution to this integral is going to come from theta in this 0, 1, which are sort of close to a rational number with small denominator, or what we call the major arcs. And the rest, that'll contribute to the main term, and then the rest will just be an error term that's of smaller order coming from the minor arcs. Okay, so what we are going to take specifically is we're going to look at those theta. The major arcs are going to be made up of those theta, which are at most k naught over n away from a over q, where q is less than or equal to q naught. So what is q naught? What is k naught? So here q naught is simply t to the delta minus theta over 10. Okay, what is delta and what is theta? Delta is the Hausdorff dimension of the group, the Apollonian group in question. So for the Apollonian circle packings, this is like 1.3056. For these other groups, it's going to be always strictly between 1 and 2. And this theta here is something that depends on the spectral gap for A. So that's what I'd like to spend a little bit of time talking about. K naught is just Q naught squared. Okay, so this spectral gap for A determines somehow how we would define the major arcs in order for the analysis to go through nicely and for the main term to actually be of larger order than the error term, and of the size that we would like it to be. Okay, so more specifically, the spectral gap in particular, what it does is it controls the error term in the following expression. So when you're going to be working with the circle method, what you end up having to evaluate is, so we're going to take our set Ft, which is this growing region inside of the Apollonian group, and we're going to split it up into cosets of A of Q. So this is just elements in A which are 0 mod Q for arbitrary Q. And so we have these exponential sums over these kind of cosets. And what you would like is that this sum is just simply the whole sum, not over the coset, but over just all of Ft times the 1 over the index of A of Q and A. That would be a natural thing to hope for. And what we get with the spectral gap is indeed, this is the case with this error term, big O of t to the 2 theta times k. Here, the k, we're assuming beta is less than k over n. And this theta depends on the spectral gap. Okay, so since I keep mentioning the spectral gap, and it's a very important ingredient in this proof, and we also have to prove that A has a spectral gap of the kind that we want. Let me tell you a little bit about that. Maybe I'll ask, are there any questions for now about this stuff? Because I'm going to move away from this for a second. Okay. Okay, so spectral gap is some value that has to do with expander families of graphs. So let me give a definition. So the kind of nicest situation to define this in is you take a family of graphs which are all k-regular for some fixed k. So in every graph, every vertex has exactly k neighbors. Finite and connected with the size of the graphs going to infinity. And we're going to take mi to be the adjacency matrix of xi. So what that means is if I have a graph xi and n vertices, mi is going to be an n by n matrix indexed by the vertices along the columns and the rows. And then the ij spot, I put a 1 if the ith and jth vertex are connected and 0 otherwise. So it's a symmetric matrix with real eigenvalues. And the eigenvalues look like this. So it's not so hard to show that the largest eigenvalue will be k from this k regularity. And the next one will be strictly smaller. And then you have these others here, all greater or equal to minus k. So I'm going to call this family of graphs an absolute expander family if there's some epsilon, such that if I look at the eigenvalue, which is largest in absolute value but not equal to k. So it's not this one, but maybe it's this one, or perhaps this last one, or second to last one. The difference between that and k is going to be always at least epsilon. So if you want to think of it just as in terms of these two eigenvalues, we're saying these two eigenvalues have to always be separated by epsilon for every xi. And so where the epsilon is independent of I. Okay, and we call, actually I'll say here, we call this epsilon a spectral gap for the graphs. Now, of course, we don't have any graphs. We have this Apollonian group. What are the graphs there? So what we do there is we take our Apollonian group A, and we reduce it modulo q for all integers q. Okay, so if you've ever seen expander graphs applied to sieves, there it's not for all integers q. You just look at square free q, but here we need all q. You take any generating set of your Apollonian group, any finite symmetric generating set, and you look at the Cayley graphs of your Apollonian group reduced mod q. It's a finite thing, together with this generating set. And by Cayley graph, I just mean that, so the vertices are just going to be the elements of the group, or indexed by the elements of the group, and two vertices are connected whenever I can go from one to the other via a generator. So I and j are connected if I times j inverse is in the generating set. So then I get this infinite family of Cayley graphs, and what I'm saying is I want there to be a spectral gap for those. Just to quickly say what this sort of spectral definition says about the graph itself and where this is coming from. So the definition for expander graphs originally in the 70s was motivated by building efficient networks of arbitrary size. So the idea is, let's say I have some subway stations and I want a model for the subway network. No matter how many subway stations I have, I want it to be very connected and also cost efficient. So I don't want to spend too much money on building lots and lots of railroads. So the cost efficiency I'll take care of by just saying, okay, I'll connect every station to exactly 4 other stations or something, or some k other stations, no matter how large the network is. That will keep the costs from growing too fast with the size of the graph. And then the connection, the sort of connectivity, we'll think of it this way. So what we'd like is that if we start a random walk at some vertex, so start at some vertex here and just start walking around randomly on this graph, we would like to know, so what is the probability that I end up at some other vertex after n steps? So it turns out that the larger this n, the closer the answer will be to just, you're equally likely to end up at any place in the graph. So 1 over the size of the graph. And if you have a very connected network, you'd like this equidistribution to happen quickly. Okay? And so how is this connected to this kind of spectral definition? Well, you can show that the probability of being at v after n steps, after starting with v naught, the difference between that and this kind of equidistributed probability is going to be, so here I'm assuming that the closest eigenvalue to k but not equal to k is just lambda 1 of mi, is going to be bounded above by lambda 1 of mi over k to the nth power. So this lambda 1 of mi over k is going to be less than k minus epsilon, where epsilon is a spectral gap in this expander family situation. And the larger the spectral gap, the faster this will decrease to 0. So again, the larger the spectral gap, the better, the better connected you are in this sense. Okay, so that's what I wanted to say about these expander graphs. And what do we show? So here is a theorem that we show, that there is some finite symmetric collection of generators S and a positive epsilon, such that if you look at the family, really, of Cayley graphs, A sub q with S sub q. By A sub q, I mean A modded out by A of q, so just the group A reduced modulo q, together with this generating S, set S reduced modulo q. We'll have a spectral gap of at least epsilon for all positive integers q, and epsilon is independent of q. Okay, and so here I should mention what has been known. So this was certainly known in our context for q square free previously by Zalehi, Golsafidi, and Varju, but not for this arbitrary q. And I should mention that in Burgan-Kontorovich's paper, where they proved the local to global principle for Apollonian circle packings, they have an appendix in their paper by Varju, who shows basically this theorem, but for the Apollonian group there. And our method of proof kind of takes his method of proof and generalizes it. So the idea, very roughly, is we first prove the statement for the following group. So this group here is, so you take a group gamma, which is a subgroup of A, and Zariski dense in SL2Z. So in our case, we could take, for example, this congruent subgroup that we know is sitting in there. But actually, even if we didn't know that A had a congruent subgroup sitting inside, if we just knew that it had a Zariski dense subgroup of SL2Z sitting inside it somewhere, that would be enough to prove the spectral gap. So the spectral gap part, you don't need this congruent subgroup sitting in your group. Okay, so you take this gamma, and then gamma conjugated by an element G, where G is some element in A, which is neither an SL2R nor an ISL2R. So you do have such an element because of the Zariski density in SL2C. Okay, so you look at the group generated by these two, and you prove this spectral gap statement for that, and then you derive the spectral gap statement for A from there, which I won't get into. But so what we will use, the fact that we will use is that this theorem, the spectral gap theorem, is true for both gamma and G gamma G inverse. So these, so it's true for gamma because gamma is inside of SL2Z, and Burgan and Varju proved this kind of theorem for subgroups of not only SL2Z that are Zariski dense in SL2Z, but also for subgroups of SLNZ, or arbitrary n. So we have that. And we kind of build the spectral gap theorem for A prime from these, the spectral gaps for these two guys here. Okay, so the lemma that allows us to do this is the following lemma of Varju's, which is in this paper Burgan-Kontorovich's in the appendix. So let G be a finite group. So in our case, G is going to be this A prime here, but reduced mod Q, with some finite symmetric generating set. And take L subgroups of G with the property that whenever you take an element in G, you can find an element from each one of these such that G is a product of those. Okay, so for us, what G1 through GL will be is there will be gamma G inverse, gamma G inverse, gamma G inverse, just alternating. So then what you have is that, so here what this lambda 1 prime is, basically what you do is, so before we had the lambda 1, you can divide out by a k for a k regular graph. That's what would lead to this lambda 1 prime in that case. So this is just a spectral gap. Just think of it that way. So the gap between the top two eigenvalues for this graph G together with a generating set S is going to be bound to be low by the minimum of the following things. So here you have this, this little thing out here, which is just the intersection of the generating set of G intersected with GI over size of S. But here what you have is the spectral gap, or the gap between the top two eigenvalues, basically, for GI, and then divided by 2L squared. Now, given that we know, in our case, that all of our GIs, they're these two groups over and over again, have the spectral gap property, we know that this is for all sort of numbers Q that we would reduce by to get down to these finite groups. We know that this is bounded below by some epsilon for each GI, okay, independent of I, and independent of the Q that we're reducing by. And then we're dividing by 2L squared. So as long as this L here is just some absolute constant, we will get a spectral gap then for the whole group, or for the family of groups we get by reducing A prime modulo Q. And so our job is basically to show that one is able to, by taking enough of these gamma G inverses, alternating, one is able to build any element of A prime mod Q in some bounded number of steps, independent of Q. Yes?
I'm sorry, did you say what lambda 1 prime is? Is that where you take the matrices based on adjacency relative to the generators S?
Yes, sorry, so I kind of brushed over that. So lambda 1 without the prime was just simply that first eigenvalue of the adjacency matrix. Here I'm just normalizing, dividing by K. In that case, yeah. So instead of having K minus lambda 1, it's 1 minus lambda 1 prime. Yeah. Okay, so this is basically how we're able to prove this theorem. And I think actually now using this kind of argument, also the third author on this paper, so Zhang together with Zalehi-Golsefidi, has proven something more general on spectral gaps. But I'd like to come back to this circle method we were dealing with before and just tell you how that story ends. So with all of this input, the spectral gap, and so on, what we're able to get, essentially, is a bound, the following bound on the major arcs. So this is the major arcs for this representation number Rn of n. A bound of t to the 2 delta minus 2. Delta is this Hausdorff dimension, so it's something between 1 and 2. And if you look at the sum of, these are the minor arcs. This is this little m sub n of n is going to be the minor arc for the minor arcs for the representation number R n of n. Sum over all n in the exceptional set. So remember, the exceptional set are those numbers which you expect to be admissible, but due to their congruence, congruences mod whatever number like 24, but they don't actually appear as curvatures. If you sum over that, that's bounded above by t to the 2 delta minus 2 times n to the 1 minus epsilon. Okay, so how does that give us what we want, which is we're trying to show that this set En is small. Well, so notice that if n is in En, what that means is that this representation number, Rn of n, is 0. It does not get represented. And so we have that this minor arc term here is just, so it's the difference between the whole representation number and the major arcs. And since this is 0, this is just the major arcs. And that's, we know, has a slower bound of t to the 2 delta minus 2. Okay, and so then what I can do is I can say, well, this term here, so I know it's bounded above by this, but also it's at least t to the 2 delta minus 2 times the size of En. Because every one of these terms is bounded by this, bounded below by this, and there's size of En terms here. Okay, well, if you divide out by t to the 2 delta minus 2 on both sides, what you end up getting is just size of En is at most n to the 1 minus epsilon, which is exactly what you wanted to show. Okay, so that's actually all I wanted to say, so I will stop there a little early.
Say in a few words, what are the obstacles for handling these minor arcs directly for large n?
Well, The minor arcs are actually not so hard to deal with. We just sort of use classical exponential sum estimates and things like that. So yeah, I don't know exactly what kind of answer.
But does that give you an asymptotic formula then for Rn of n?
An asymptotic, well, no, so you only have, no, I mean, so first of all, okay, so there's some things that I'm concealing a little bit. First of all, so you only have this upper and lower bounds for the major and minor arcs, so I'm not sure.
I guess I'm just interested in
Yeah.
what the scope is for actually proving the local to global principle.
I don't think this could be taken to actually prove the whole local to global principle. Yeah, and the other thing I should mention, I don't know if this is of interest, but we don't actually, so here when I write m sub big N of little n, this is actually true for n between n over 2 and n. And then we kind of divide the interval between 0 and n dyadically and work with every one separately, which I think also may complicate trying to prove it directly.
So if I recall right, when you introduced the spectral gap, you asked for the gaps between each of the eigenvalues to be bounded below.
No. So what I said was that the gaps between, so you look at the largest eigenvalue closest to k, but not equal to, in absolute value, but not equal to k.
Okay.
And you need that to be, bounded away from k, basically.
Okay, so it's just the...
It's just those top two. So the idea is that you want to use the fact that all of the other eigenvalues will be at least epsilon away from the top one. You want to use that, then that's enough. Yeah.
So, so classical applications of a certain method involving exceptional sets in things like Waring's problem, something which is intermediate between just getting an exceptional set for all integers, kind of thing that Tim was asking about, which is each individual n, is to restrict the ends to, say, a polynomial sequence.
Okay.
The harmonic analysis works pretty well for these fit sets, so in many situations you still get an exceptional set even when you restrict to whatever your favorite polynomial is. But do you think there's scope for restricting the lengths to
So I think you might get like a better epsilon or something here, but I still don't think you would actually end up getting that the set of exceptional guys is finite somehow, if that's what you're asking. Oh,
I'm just saying, here you're getting an exceptional set
yes.
for all integers. So it's a stronger statement if you're getting an exceptional set when you're restricting
Oh, I see. I see.
the set.
I see. I think that I have not at all thought about this, but my gut reaction is that probably you could make that work out as well.
Kind of morally closer to
Yeah, no, that's true. It would be morally closer. Thanks.
Well, let's thank Elena again.